Same thing, we are going to answer the first two questions, okay? Find the increasing decreasing interval for f and also local maximum or minimum for f, okay? So as we talked about already, okay, so first we know c of x equals this. We need to differentiate c, right? That gives us the 4/3 x to the what? 1/3 plus 4 times by 1/3 times x to the what? 1/3 minus 1 gives us negative 2/3. Okay, so this is the derivative. Okay, however, this does not look very clear, right? So we have a 4/3, we have a 4/3. So I would say let me pull the 4/3 out first, and then we have x to the 1/3 plus x to the what? Negative 2/3. Alright, now from here, okay, we cannot see, right? Because negative 2/3, we can have a 1 over x to the 2/3. So we should have something on the denominator. And this is 1/3. So how to simplify this part? I saw a lot of you guys are getting it. Okay, yeah, got it correctly. Okay, so first third, we are pulling the x to the negative 2/3 out, and then inside of the parentheses we will have x times by x to the negative 2/3 give us x to the 1/3, right? So this is x to the first power. If we're pulling the x to the negative 2/3 from this term, we'll have a 1 left, right? So this will equals what? 4/3 on the top give us x plus 1. On the bottom it gives us x to the what? 2/3. What is x to the 2/3? X squared cube root. Or you can say square root of x to the cube. Either way, okay? So on the bottom it gives us this, okay? Alright, now this is C prime. In order to find the critical numbers, either we let the numerator equal 0 or with the denominator equal 0 give us what? The critical numbers, right? So that means C prime of x equals 0 implies what? X plus 1 has to be 0, right? Implies x equals negative 1. Oh, a critical number, okay? And then when C prime of x does not exist, it implies what? Denominator equals 0, which is x to the 2/3 must be equal 0. And it will implies what? Only when x equals 0, 0 to the 2/3 equals what? 0. So these two are our critical numbers, and we have to check whether we are in the domain of our function or not. What is the domain for our original function? X to the 1/3.
It's not restricted.
Not restricted. How about x plus 4?
Not restricted.
So what is the domain for the original function?
All real numbers.
Yes, you're right. Domain all real numbers. There's no restriction for x. Means x could be all real numbers. Okay. So now we have these two values. Real number line x. Okay. So we're gonna mark them on the real number line. So negative 1 and 0 will divide this entire real number line by how many intervals? Open intervals? 3, right? The left one, negative infinity to negative 1. Negative 1 to 0, and 0 to what? Infinity. Right? Now let's test. On this interval, what key numbers do you want? Key number.
I use negative 1 because it's convenient. And I use...
You use negative 1.
Oh, so I use negative 2.
Yes, negative 2.
I then use negative 1/2, and I used 1.
How about negative 3 instead?
That's fine.
Yeah, anything works.
Any number is greater than 0 works. Okay, then I'm going to test the sign of the C, okay? The sign of C. Okay, so when x equals negative 2, plug this negative 2 back into here. See, when x equals negative 2, is this result positive or negative?
It's going to be positive.
Careful, on the bottom. we should have a negative 2 cube root of this negative 2 square, right? What is the sign for cube root of negative 2 square? Always positive. Why? Because we're always going to square this whatever number. So on the bottom, it's always going to be positive. However, on the top, it give us what? Negative number, right? So eventually, negative divided by positive give us what? Negative, okay? So here, just now, Grant, I saw you have a different sign, right? So it is going to be negative, okay? How about when x equals negative 1/2? Well, this is negative 1/2. Remember, this is always going to be positive, right? Negative 1/2 plus 1, positive, times 4, positive, right? Positive over positive. How about on this interval? C prime is positive, means it's, C will increase, okay, on this interval. And how about when x equals 1? How about the sign? Positive or negative? Positive, right? So positive here. Alright, so we are going to say,
I have a question.
Sure.
Can you get rid of the 4/3 up there and just make it, because you factor it out and move to the other side of the 0?
this 4/3, we just keep it, right? It doesn't matter for the result of anything, because 4/3 is a constant.
That's what I did, which is I did it right.
Yeah, yes, you keep it, right?
No, I got rid of it.
No, you don't get rid of it, because in the next step we will have to keep on differentiating the c. You don't get rid of this 4/3. Okay, so it's not we're not just solve for c prime of, c prime of x equals 0. You can't get rid of the 4/3. Okay, because only x plus 1 equals 0 matters.
That's what I thought.
Yeah, but c prime of x is this.
Well, I understand.
Yeah. Alright, so we have a conclusion that this is question A. F is what? Decreasing. Oh, C, sorry. This is function C is decreasing on the interval from where to where? Negative infinity to negative 1. And it is increasing this and that, okay? How about C prime of 0? What is C prime of 0? Is it positive or negative? When x equals 0, when x equals 0 does not exist, okay? So I would say, C is decreasing on this interval and is increasing on two separate intervals, okay? On what? Negative 1 to 0 and what? 0 to infinity. We're not talking about when x equals 0, okay? When c equals 0. When x equals 0. Because when x equals 0, c prime of 0 it does not exist. So it does not give us a positive, okay? C prime of 0 does not give us a positive sign. So we say increasing on these two intervals. You guys, this good, everybody? Now, okay, let's check local maximum, local minimum. Remember just now we got two critical numbers. One is x equals negative 1, okay? And x1 is here, okay? We know that on this interval, our function is what? Decreasing, okay? On this interval, function is increasing. And on this interval, function is what? Increasing, right? So do we have any local maximum, local minimum?
You have a local minimum at negative.
We have a local minimum at when x equals what? Negative 1. And it's indeed, see, when x equals negative 1, c prime of x equals 0 means we have a horizontal line, right? Yeah, slope of the tangent line is 0, right? However, we cannot say when x equals 0. If x equals 0, c prime of x does not exist. Okay, so, and see there's no change of signs when x is less than 0 and greater than 0, so there's no maximum or minimum at when x equals 0, no, okay? But there will be a local minimum c of negative 1 will be a local minimum, okay? C of negative 1 equals, let's plug in C of negative 1 into the original function, okay? So I will say here, negative 1 to the 4/3 plus 4 times negative 1 to the 1/3 and see what we get, okay? Negative 1 4/3. Negative 1 to the first power, 1. Cube root 1. What is cube root of negative 1? Negative 1 times 4. Okay, so C of negative 1 equals negative 3 is what? The local minimum value of function C. You guys, was good? Alright, so this is the first part of this section, first order derivative, okay? Are you ready for the second order derivative? You are? Let's move on to look at the second order derivative, okay? Alright, so what does f prime prime say about f? Okay, I'm going to ask a volunteer to read both of this definition and this definition. We'll read both definitions, okay? Okay, now let me see whose turn. Who want to read? Any volunteer? Tyler?
If the graph of f lies above all of its tangents on an interval, it is called concave upwards on one. If the graph of f lies below all of its tangents on the interval 1, then it is called concave downward on one. A point P on a curve y equals f of x is called an inflection point if f is continuous there and the curve changes from concave upward to concave downward, or from concave downward to concave upward in P.
Okay, very good, thanks, okay? So this is the definition for concave upward, concave downward, okay? So what kind of curve is called concave upward? Yeah, like this, okay? Whatever, okay, like a bowl, like opening up, okay, bowl opening up, okay, and then how to check it mathematically? If we draw tending to any point, okay, to tangent lines are always below the graph of f. Then it is what called a tangent upward. Or you just know a bowl opens up, okay, yeah. That's a concave upward, okay? How do you understand a concave downward? A bowl facing down, okay? Or if we draw any tangent lines to the curve, it's always on top of what? It's always above its tangents, okay? So see, F always lies above of tangents, called concave upward. F always lies below the tangents, is called what? Concave downward. Okay? Alright, the next definition says a point P is called the inflection point, okay? If, say for example, the curve looks like this, concave downward, and then change to concave upward at this point P, then this point P is called what? Inflection point. Or previously, it is downward, it is upward, and then it changed to be what? Downward. So at this point P, okay, from upward to downward, or from downward to upward, this kind of point is called what? Inflection point. You guys see that's good? Okay, so we know concave and also we know inflection, and then what does derivatives helps understand the concave upward or downward, okay? So we have this concavity test. I'm going to ask a volunteer to read this test for us, Grant.
If the second order derivative of x, f of x I should say, is less than 0, for all x in the specified segment, then the graph of f is concave upward on that segment. If the second order derivative of x is, sorry, I think I meant to say more than, less than 0,
Yes.
for all x in the specified segment, then the graph of f is concave downwards on that segment.
Very good. The first one is f, second order derivative positive. Then we have what? Concave upward. Okay, so later, okay, your mind have to remind you, okay, second order derivative positive is connected to what? Equivalent to what? Oh, concave upward graph. Second order derivative less than 0 is equivalent to what? A concave downward graph. You may ask why. I'm going to show you. What is a second order derivative? Yes, you're right. Second order derivative is a derivative. Okay. So just now we say that, okay, yeah, okay, so, alright, say, this is one tangent line, right? This is another tangent line, so this is f prime of x1, this is f prime of what? x2. I'm asking you, which slope is bigger? We have two tangent lines, which slope of the tangent line is have a greater value?
Sub 2.
F of prime of x2, right? So you see that f prime is what? Increasing, right? See, f prime is here, then increase, f prime increase because the slope increases, right? Like this, okay? So, if f prime increases, when f prime increases, it will implies what? The derivative of f prime is what? Positive than 0. Remember, previously, f is increasing is equal to f prime is positive, right? Now, when f prime increases, it's equivalent to what? The derivative of f prime is positive. What is the derivative of f prime? F prime prime. Guys, do you see that? Okay, so that's why second order derivative positive gave us what? Concave upward. Okay, because we can tell concave upward give us what? Oh, the slopes of the tangent lines are increasing. Guys, do you understand that? Okay, now similarly, downward. See, this is a tangent line, this is a tangent line. The slope of this tangent line is greater than the slope of this tangent line, right? So the f prime is decreasing. So f prime prime is what? Less than 0. And then we have what? Concave downward graph. Everybody smells good? And then eventually, this is proving, okay, geometry proving. But what I need you guys to know, positive second order derivative equivalent to concave upward. I require you guys to memorize it. Negative second order derivative equivalent to what? Concave downward graph. Okay, so we use the conclusion directly later, right? Alright, now let's move on to look at our last test, okay, in this section. It's called a second derivative test. We learned the first order derivative test, and then now let's see second derivative test. Also can help us to do what? Local maximum, local minimum, right? Remember first order derivative give us local maximum, local minimum, right? So what do? Find f prime of c equals 0, then we check what? We check whether f prime of x is less than 0, and then, you know, change signs, right? Now, second derivative test is telling us how to use a different way, use second order derivative to find local maximum and local minimum, okay? We want to read this test. Who has not read for us today? Dave?
Suppose f prime prime is continuous near c. If f prime of c is equal to 0 and f prime prime of c is greater than 0, then f has a local minimum at c. If f prime of c is equal to 0 and f prime of c is less than 0, then f has a local maximum at c.
Very good, thank you, okay? So let's see how second derivative test is telling us. If f prime of c equals 0, that means what? C is a critical number, right? Of course, C is a critical number. And also we know that at C, the derivative of the graph is what? Derivative of the tangent line, f prime of C equals what? 0 like this, or C, right? So if f prime of C equals 0, we know that C, okay, the slope of tangent line is, equals 0. Alright, it says, if f prime of C is positive, what does this mean? The graph is going to be what? Concave upward or downward? Upward. So, if f prime of C is positive, means we're going to have a concave upward graph.
Oh, because I get it. Because
So we'll have what? Local minimum. Because when it opens up, we should have a local minimum value, right? This is a case A. Okay, yeah, I should write this is case A. How about case B? F prime of C equals 0, but F prime of C is less than 0 means what? Graph is concave downward, right? So F prime of C is less than 0. So if the graph concave downward, we should have what? Local maximum. This is case B, okay? You guys see that? Alright, so this is a second derivative test, okay, to find a local minimum and local maximum. So in the exam, if I'm asking you to find local maximum, local minimum, it doesn't matter which test you're using. You can use the first test if you feel comfortable. You can also use what? Second test. So guys, for the same question, how can I find the local maximum, local minimum of f? Just now we know f prime of 4 equals 0, right? We only talk about the derivative equals 0. We do not talk about the derivative does not exist, okay? So if f of 4 equals 0, then whether f of 4 is local maximum or local minimum, what do? Just need to differentiate f secondly, okay? And then check f prime of 4 positive or negative. If f prime of 4 is what? Greater than 0, then we'll have this case, right? F of 4 will be what? Local minimum. If f prime of 4 is less than 0, we'll have this kind of case, then capital F of 4 will be what? Local maximum. You guys see this good? So you can also use the second derivative test to find the local maximum, local minimum value. But here I'm not going to repeat it, okay? But let you guys know, both this test and this first derivative test, they help us to find what? Local maximum, local minimum. And I personally think the second derivative test is more direct, because remember from the previous question, we also talked about f prime does not exist, right? So now you know we don't have to worry about that for the second derivative test. The local maximum, local minimum only happens when f prime equals what? 0. It will not happen at when f prime does not exist. Well, this works for both first and second derivative, okay? And for the second derivative test, once you get f prime of equals 0, you get x equals some critical number, you only need to differentiate f one more time for find a second order derivative. And the test, the second derivative added this number to see whether it's positive or negative. Then you will get a local maximum or minimum.
But you have to find where f prime doesn't exist and get the critical number anyway, right?
Well, for local maximum, local minimum, you don't have to worry about this. And then you see, eventually we have f of 4 local maximum here. See, this is when f prime equals 0. And then from the previous question, remember we found a 2, right, equals 0 or does not exist. So x equals -1, x equals 0. So eventually, f of c of -1 give us what? Local maximum, local minimum. So for local maximum, local minimum, eventually you will see we'll only worry about when the derivative of the function equals 0. When the derivative does not exist, eventually it will not be either local maximum or local minimum. Okay? Alright, so I would say that, okay, so we're done for all of the knowledge part about test, okay? So let's keep on working on our questions, okay, the questions. Okay, so this is question, the first question, okay? Yeah, I will pause it and then initiate another one, okay?